In physics, out of the several forces that we analyze, there is a particular type of forces, or there is a particular classification of forces that is important for us. So this particular classification divides forces into conservative and non-conservative forces. So conservative forces are so named because they conserve the mechanical energy of the system. That is, they do not dissipate energy in the form of heat, light, sound, or in any other non-mechanical format. So they conserve the mechanical energy of the system. Whereas non-conservative forces may not conserve the mechanical energy of the system. They may sometimes dissipate, sometimes they may not dissipate, but they have no obligation to conserve the mechanical energy of the system at any given point. So this is the colloquial or the understanding wise definition. So basically conservative forces, what do? They conserve the mechanical energy. Mechanical energy is conserved. Non-conservative forces may not conserve the mechanical energy. Alright. Now the defining characteristic of conservative forces. The work done for conservative forces is path independent. So let us say a particle moves from point A to point B. It may adopt several paths to do so. So it may go as per path 1 or as per path 2, or it may go as per path 3 or any of the other paths basically. So there are infinitely many possibilities to start from point A in space and to reach point B in space. So these are the several paths that are possible, along with infinitely many others. So the work done is going to be independent of the path. So work done is path independent. In case of conservative forces. In case of non-conservative forces, the work done may be path dependent. So why are we saying maybe? So in most of the cases it is. In some few cases it may momentarily, in that particular example, be independent of path. However, that does not mean that for that particular force it will be always independent of path. But whereas in case of conservative forces, work done is inevitably always independent of the path basically. So here in this case, work done in path 1 is going to be the same as work done in path 2 is going to be the same as work done in path 3. Whereas if we have several paths 1, 2 and 3, where the particle is moving from point A to point B in a non-conservative force field, then work done of path 1 is in general not equal to work done of path 2 is in general not equal to work done for path 3. So here the work done is equal. How to know whether a force is conservative or not? So conservative forces have this particular characteristic, a very important one. So I'm writing down a mathematical expression over here. This is called as the curl of the force F. The curl of the force F. It is given as the cross product between the del, which is the reverse triangle shown over here, and the force F. So this is the partial derivative with respect to x, this is the partial derivative with respect to y, and the partial derivative with respect to z. So this is the x component of the force, the y component of the force, and the z component of the force. So if this happens to be equal to 0, then the force is necessarily conservative. Another method of checking is whether the work done is path independent. So if the work done is path independent, if you start at a particular point P and return back to the point P, so this you have completed the cycle. So the net work done has to be 0 basically. So when we say that the work done is path independent, the work will depend only on the initial and the final coordinates basically. So the work will be a function of the coordinates of point B minus the function of coordinates of point A. So when we say that the curl of force F is equal to 0, then after expanding here we get curl of F is equal to, this is curl of F is equal to I cap partial derivative with respect to y of the z component of force minus partial derivative with respect to z of the y component of force minus j cap, as is customary to open determinants, minus j cap partial derivative with respect to x of the z component of force minus partial derivative with respect to z of the x component of force plus k cap. So this happens to be the expression of the curl. Each of these brackets has to be 0. See, this bracket, because the net value of the curl is 0, so no component can survive if the force is to be conservative. So k cap partial derivative with respect to x of the y component of force minus partial derivative with respect to y of the x component of force. So what do we mean by partial derivative? Essentially what partial derivative means is that we differentiate only with respect to the particular given variable, assuming all other variables to be constants in that particular case. As we are differentiating, let's say we are differentiating with respect to x, then in that case x is assumed to be the only variable. So in Fz, in the expression of the z component of this force, maybe x, y, z, all the three may come. However, we assume that y and z are momentarily constant because we are differentiating only with respect to x. So we consider only x to be the variable. So non-conservative forces in general dissipate mechanical energy. They may not conserve mechanical energy, even if sometimes in some cases they do not dissipate mechanical energy for particular instances. Now, the most interesting aspect of conservative forces happens to be the fact that a function called as the potential energy function can be defined only for conservative forces. The potential energy function can be defined only for conservative forces, and the definition of the potential energy function is delta U is defined as the change in potential energy is equal to negative of del dot F. So this is the divergence of F. This can be in Cartesian coordinates simplified as negative of partial derivative with respect to x of the x component of force, negative of partial derivative with respect to y of the y component of force, negative of partial derivative with respect to z of the z component of force. We may take the negative sign outside and we may say that this is equal to ddx of fx plus Actually, this is called as dou y of fy because it is partial derivative, not exactly normal derivative, plus dou z of fz. So this is delta U, change in potential energy of a system. This is how it is defined to be. So for conservative forces, if let us say only conservative forces were acting on a system, so what happens is work done is path independent.